Welcome to our project on insurance pricing forecast using XGBoost Regressor. In today's data-driven world, insurance companies need accurate and reliable tools to forecast healthcare costs. Traditional methods often struggle with complex data relationships, and that's where machine learning, especially XGBoost, comes into play. Let's dive in and explore how machine learning is transforming the future of insurance pricing. Development process. Step 1. Data collection. Collect healthcare data with features like age, BMI, and smoking status. Step 2. Data preparation. Clean and code and transform the data for model training. Step 3. Model building. Train linear regression and XGBoost models to predict costs. Step 4. Model evaluation. Measure accuracy using RMSE and MAPE scores. Before we start with the code, head over to Google and search for Insurance Pricing Forecast AIOnlineCourse.com. On AI Online Course, you'll find the complete guide with detailed explanations and well-structured content. Now, let's dive into the code. Mounting Google Drive. Connect your Google Drive to Collab, allowing access to your files at Content Drive after authorization. Installing essential libraries. These pip install commands install popular Python libraries like NumPy, Pandas, Scikit-learn, XGBoost, and others in Google Colab. They are used for data handling, machine learning, optimization, and visualization. Import essential libraries. Now, import key Python libraries for data handling, visualization, machine learning, preprocessing, and model optimization, preparing the environment for building and evaluating ML models efficiently. Load dataset from Google Drive. Now, read the insurance dataset.csv file from Google Drive into a Pandas data frame named Data for Analysis. Preparing features and target. We separate the dataset into input features X and the target variable Y, which you want to predict. Plotting target distribution. Creates and displays a histogram of the charges column using Plotly, showing the distribution of insurance charges with 50 bins. Selecting numeric features. Now, extract all numeric columns from the feature set X and list their column names. Plotting correlation heat map. Creates a heat map to visualize the correlation between numeric features, helping to identify relationships and dependencies in the data. Selecting categorical features. We identify and list all categorical columns in the feature set X. Visualizing target distribution by category. Creates box plots for each categorical feature, showing how the target variable varies across different categories, helping to spot patterns and outliers. Visualizing relationships between numeric features. Now, generate scatter plots for each unique pair of numeric features to visually explore relationships, trends, or potential correlations between them. It helps identify patterns, clusters, or outliers in the data. Creating a scatter matrix. We use seaborn.pairplot to create a scatter matrix, showing pairwise relationships between all numeric features. It helps visualize correlations, distributions, and potential patterns in the dataset. Interactive correlation heat map. Uses plotlyspx.imshow to display an interactive heat map of the correlation matrix for numeric features in X, helping to visually identify feature relationships and multicollinearity. Chi-squared test for categorical features. We check if each categorical feature is significantly associated with the target using the chi-squared test. A p-value less than 0.05 indicates a meaningful relationship. All three categorical features, sex, smoker, and region, have a p-value of 0.0000, indicating a statistically significant association with the target variable charges. This means these features are likely important predictors for insurance charges. Install and import Penguin. ANOVA test with Penguin. This code checks if the average age differs significantly across BMI groups. Note, BMI should be categorical for the test to work properly. Data preparation and transformation. Now, we split the dataset into training and testing sets, drop irrelevant columns, and apply one-hot encoding to categorical features. It then removes the redundant encoded column smoker no. Finally, it applies a Yeo-Johnson power transformation to the target variable to normalize its distribution, improving model readiness and performance. Plot histograms of the transformed target variables to visualize their distribution after normalization. Linear regression model training. Now, train a linear regression model on the transformed target yTrain-T using sample weights based on the original target values to emphasize samples with larger targets during training. Training model evaluation evaluates the model on training data by predicting, reversing the target transformation, and computing MSE, RMSE, MAPE, and our superscript 2 metrics. The model explains 76% of the variance. Our superscript 2 equals 0.761, but has a high average percentage error. MAPE equals 74.34%, indicating a decent overall fit with some large relative prediction errors. Test model evaluation. Now, it predicts on the test data, reverses the target transformation, and computes evaluation metrics, MSE, RMSE, MAPE, and our superscript 2, to assess the model's performance on unseen data. The model performs well on test data, explaining 76.4% variance. Our superscript 2 equals 0.7644, with a MAPE of 66.68% and RMSE of 5,930.10, showing good generalization. Evaluation summary and actual versus predicted plot. Displays a table comparing train and test metrics MSE, RMSE, MAPE, our superscript 2, and visualizes model performance by plotting actual versus predicted values on the test set with a reference line indicating perfect predictions. Residual analysis with Q-plot plots a Q-plot of residuals to check if they follow a normal distribution, helping validate linear regression assumptions. Q-plot for test residuals displays residuals to check normality. Alignment with the 45 degrees line suggests the model's errors are normally distributed. Residual distribution plots. Now, create side-by-side histograms with KD for both training and test residuals. It helps visualize how the errors are distributed and check for symmetry or skewness, aiding in evaluating model fit and assumptions. Train test split. We split the dataset into training and testing sets, with 33% of the data used for testing and a fixed random state of 42 to ensure reproducibility of the split. One-hot encoding applies one-hot encoding to convert categorical features into numerical format. The encoder is fitted on XTrain and then applied to both XTrain and XTest to ensure consistent transformation. XGBoost pipeline with our FE and Bayesian optimization. Now we set up a machine learning pipeline combining recursive feature elimination and XGBoost Regressor and tune hyperparameters using Bayesian optimization via Bayes Search CV. The pipeline performs feature selection and model training, while the search explores various values for number of features, number of trees, depth, regularization, learning rate, and gamma to minimize root mean squared error, fitting the optimized XGBoost pipeline. This line fits the Bayes Search CV-based pipeline on the training data, performing recursive feature selection and hyperparameter tuning with cross-validation to find the best XGBoost model configuration that minimizes RMSE. Retrieve and sort cross-validation results. Converts the cross-validation results from the Bayesian search into a data frame and sorts it by the best performing models based on their rank CV results, holds the sorted hyperparameter tuning results, showing performance and rankings for each tested configuration. XGBoost model evaluation on training set uses the best XGBoost model from Bayes Search CV to predict on the training data and calculates key evaluation metrics RMSE, MSE, MAPE, and our superscript 2 to assess model performance on the training set. The optimized XGBoost model performs very well on the training data, with a low RMSE of 3076.05 and a high R superscript 2 of 0.9320, indicating it explains 93.2% of the variance. The MAPE is 20.41%, showing relatively low average percentage errors. Overall, the model fits the training data accurately. XGBoost Model Evaluation on Test Set evaluates the optimized XGBoost model on the test data by calculating RMSE, MSE, MAPE, and our superscript 2. It helps assess how well the model generalizes to unseen data. The XGBoost model performs well on unseen data with an RMSE of 4292.06 and our superscript 2 of 0.8766, meaning it explains 87.66% of the variance. The MAPE of 24.29% indicates moderate average prediction error, showing strong generalization with slightly higher error than on the training set. Comparison table of training evaluation metrics creates a data frame comparing the performance of linear regression and XGBoost models on the training set using key evaluation metrics. It provides a clear side-by-side view to assess which model performs better. Actual versus predicted plot visualizes the XGBoost model's predictions on the test set by plotting actual versus predicted values. The dashed diagonal line represents perfect predictions. Closer points indicate higher accuracy and better model performance. Model comparison and selection based on training metrics. Now, create a table comparing evaluation metrics of linear regression and XGBoost and prints a detailed comparison line by line. Here's a summary of the results. XGBoost outperforms linear regression across all evaluation metrics. It has significantly lower errors and higher explanatory power, making it the better model for this task. Visual comparison of model performance creates bar plots to visually compare root mean squared error and our superscript 2 for linear regression and XGBoost. The left plot shows RMSE. Lower is better, indicating smaller prediction errors. The right plot shows our superscript 2. Higher is better, reflecting how well the model explains target variance. This helps clearly identify the better performing model at a glance. Now, calculates how many of the XGBoost model's predictions on the test set fall within $10,000 of the actual values. It then computes the percentage of such predictions, giving a practical measure of model accuracy in real-world terms. There's a small mismatch between the comment and the print statement. The code calculates the percentage within 30%, but the print message says 20%. That means 8% of your XGBoost model's test predictions are within 20% of the actual charges, showing good relative accuracy on most samples. We successfully built the insurance pricing forecast using the XGBoost Regressor. This project helps predict healthcare costs more accurately, enabling insurance companies to set fair and profitable premiums. With advanced preprocessing, hyperparameter tuning, and thorough evaluation, our machine learning approach proves to be far more effective than traditional methods. For more exciting AI projects, stay tuned with us, and don't forget to visit AIonlinecourse.com. That's all for today's video. Thank you for watching. If you liked this project, don't forget to hit the like button and subscribe for more tech tutorials.